So in this video, we're going to be looking at specifically ionic bonding and some of the details associated with that type of bond formation. So an ionic bond consists of basically two differently charged atoms that are attracted through electrostatic interactions. So basically what that means is we have one thing that's positively charged and one thing that's negatively charged, and they attract each other to form an ionic bond. Now, this usually occurs between a metal and a nonmetal, such as, let's say, sodium ion, okay, and a chloride ion to give us NaCl. Okay, however, we could also see an ionic bond form between a ion that is positively charged that is not a metal, okay, and a nonmetal anion to give us this type of ionic compound. So basically the concept is that you have a positively charged ion interacting with a negatively charged ion. Most of the time that'll be between a metal and a nonmetal. However, there are exceptions as we see here. So when we actually form an ionic compound, we need to think about what actually physically happens. Okay, so what physically happens is that we first start out with two individual neutral atoms. Okay, and the neutral atoms are basically going to either transfer or accept electrons depending on their specific needs. So if we go ahead and look at sodium atom here, sodium has one electron in its outermost shell. Okay, so in order to be like its nearest noble gas, sodium is willing to give up an electron. On the opposite side of that, chlorine has 7 valence electrons and is in need of an extra electron in order to be like its nearest noble gas. So in order for both of them to obtain the octet that will confer stability, the sodium is going to transfer an electron to the chlorine, and subsequently you're going to form a sodium cation and a chloride anion. Now, the positive and negative charges of these ions causes that electrostatic interaction, and the attraction between these two ions is what creates that ionic bond. So, as just a rehash of what we just talked about, basically what's going to happen is your atoms are going to lose or gain electrons, and basically they're going to do that depending on what they need. The attractive forces, or those electrostatic forces that occur, are going to happen because of the opposite charges of the ions that are produced. And the strength of these interactions, which is a new concept, is going to be dictated by the size of the charge. Okay, so the larger the charge on the ions, the stronger the electrostatic interactions. And the stronger the electrostatic interactions, the stronger the ionic bond. Another way to look at this type of bond formation is to look at it with respect to ionization energies and electron affinities. So atoms that have low ionization energies, which are typically metals, are going to be those that want to give away electrons. And atoms with high electron affinity, the ones that are going to be the ones that accept those electrons from those metals. So basically, we're going to be forming ionic bonds when you have an element that wants to give up an electron in order to be like its nearest noble gas, and one that wants to accept it. Now, in order for it to give away electrons, it needs to have a low ionization energy. That needs to be an easy process. And elements that need to accept electrons, or want electrons in order to have their octet, need to have a high electron affinities in order to facilitate that type of transfer. Ionic compounds are typically crystalline and very, very structured. If you look at the diagram here, the sodium chloride lattice structure, you'll notice that you have a repeating set of ions. You have chloride, sodium, okay, and this continues all the way down through and across the solid. Okay, so this repeating structure, or this repeating lattice, is what we come to expect or anticipate with ionic solids. In that same thought process, they also are very brittle and have high melting points. The reason why they're very brittle is because any disturbance in the interactions between the ions in the lattice lead to repulsive forces. So if I were to take a hammer and hit the row of atoms right here and basically shifted each one of these atoms down by one, what you would end up with is negatively charged ions being in close proximity and subsequently repelling one another. So whenever the structures of these ionic solids are disturbed, you end up with a crumbling or basically a disintegration type result because of those interactions. Now, the high melting point is due to the high lattice energy because of the overlapping and sequential organization of the interactions between the sodium and chloride ions, or the positively and negatively charged ions. And we'll talk more about this feature here in a second. So lattice energy, or the energy associated with the structures that form in ionic solids, usually have an enthalpy of formation that is exothermic, meaning that when ionic solids form large structures or interact in a repeating way to form a lattice, energy is released. And so the energy that's released actually comes from the formation of the crystalline lattice. The energy released when the two ions come into close proximity and interact is basically multiplied by the three-dimensional structure that was seen on the previous slide. So basically, when the negative and positive ions come together, they release that energy, and the structure that we produce is a very organized ionic solid. So the lattice energy is actually the energy required to completely separate ions in an ionic solid. So when we're talking about lattice energy, we're talking about the energy that we would put in order to break an ionic solid apart. So in this case, the lattice energy that we see is positive because you have to put energy in order to break these apart. Now, when the structure actually forms, when you have a lattice that forms in an ionic solid, you're actually looking at the reverse process in which the two ions come together and form the ionic bond. Okay, so by reversing that process, we know our sign is going to change, and the coming together of these ions releases energy and is subsequently exothermic. Now, the magnitude of the lattice energy of an ionic solid depends on a couple of features. It depends on the ions' charge, it depends on their sizes, and basically the arrangement within the solid. So these features are going to affect and alter the overall lattice energy of the solid. So if we look at this equation here on the right-hand side, it represents the potential energy associated with two interacting ions. And what you see here is you have Q1 and Q2. This represents the charges of the individual ions. Okay, D is the distance between the ion centers, and K is a constant. So if you look at this equation here, the bigger the Q values, right, the larger your overall energy, potential energy is going to be. And the smaller the distance between the ions, okay, the larger the potential energy is going to be. So the magnitude of your lattice energy is going to depend on charge and size of the ions. Now, the biggest factor in this content, or in this calculation, is the actual charge of the ions. So the larger the charge, typically the larger the potential energy of that interaction. Okay, and the reason why that's the case is because the size of various ions don't really vary quite as drastically as the charges potentially can. So let's go ahead and let's look at this question here. Okay, so they want us to arrange sodium fluoride, cesium iodide, and calcium oxide in order of increasing lattice energy. So what we would look at here is we would first consider the charges of the ions present. Okay, so if we look at calcium and oxygen, calcium is a 2+ ion, oxygen is a 2- ion. Okay, cesium is going to give you a +1 ion, iodine is going to give you a -1 ion, sodium is going to give you a +1 ion, and fluorine is going to give you a fluoride ion and a -1 ion. So if we look at these three compounds and we look at the overall charges, we immediately know that the calcium oxide is going to give us the largest lattice energy, and that's because it has the largest charge values when comparing the three. So now we need to figure out whether cesium, iodide, or sodium fluoride is going to be the next largest. So what we're going to consider here now, because the charges are the same, is the actual size of the ions. So if we look at our periodic table, we look and we see that cesium is about 4 rows below sodium on the periodic table, and iodine is below fluorine on the periodic table. And we know that our size trends state that the lower on the periodic table we are, the larger the atom or ion. So we know that cesium and iodine have larger radii. A larger radii is going to lead to a larger internuclear distance, and subsequently is going to make our denominator larger. Our denominator being larger is subsequently going to make the overall potential lattice energy smaller for cesium iodide. So cesium iodide is going to be our smallest, okay, in terms of lattice energy. Sodium fluoride will come next because the atoms are slightly smaller, or excuse me, the ions are slightly smaller than the ones in cesium iodide. And calcium oxide is going to be the one with the largest lattice energy because it has the largest overall charges. So if you want to understand a little bit more about these attractive forces and lattice energies, you can take a look at page 295 in your textbook. It goes through a nice procedure of analyzing how Hess's law is connected to the formation of a crystal lattice. I think you may find it very informative.